Thank you. Thank you so much for the kind introduction. And I'm very excited to be giving this talk. And I'm sorry I wasn't able to make it in person, but I had random issues pop up. So today we will be talking about Bayesian optimization, and we're going to go from simple stuff with Gaussian processes and then go to advanced stuff, hopefully, if time allows, with transformer architectures. So let's just frame what we are going to be working on today. Our goal is we would like to solve a problem of this form. So we would like to maximize, with respect to some variable x, a function f of x, and that function f of x has constraints with respect to the variable x. Now, if you look at this problem, you would say, yeah, okay, so what's new? You know, like this problem has been studied for a very long time in the literature, right? However, we have two unique properties of this problem that make it more difficult than standard optimization questions. So the first property is that the function itself is a black box. So what I mean by black box, we don't know its equation. Does not necessarily mean it is differentiable. So you cannot really write down, kind of the equation of this function in a closed form. And the second important thing is that this function is very expensive to query. So meaning because we don't know it, right? Like we don't know this function, we want to try different variables of x to understand what this function says. But you cannot do a lot of trials, right? Because this function is expensive either in time or in money. So the same goes to the constraints, where we also assume that the constraints can sometimes be black box, so we don't know these constraints in closed form, and they are also expensive to query. So now we have a problem where we are trying to maximize a function subject to constraints, but that function, we don't know, its form, its equation, and also it is expensive to evaluate. So in other words, it's a black box, right, function, and there's a lot of money involved when you evaluate that function. So what would we like the properties of our solver to look like, when trying to solve this function? Well, because we don't know this function, right, we would like the solver to be data-driven based, right? So the idea is that because I cannot, take a gradients or use autodiff and so on, because I don't know, it's a black box, I don't know the equation. What I would like to do is I would like to have a solver which will query this function. So it will ask, different position of x, and then get feedback of the value of x. And based on this data, I would like it to improve, right? So I will try this variable of x, then my function says, oh, that's your function value f of x. And then based on that, I would like to improve my next choice of x. But more importantly, right, I want the solver to be data efficient, right? Because the function is very expensive to query. So I cannot go standard machine learning on it, right? Where I just assume I have gazillion data points for this problem, because to collect these data points, it's a lot of money and a lot of expense. So not only that I want a data-driven solver, right, but I also want a solver that will reduce how many queries I will ask from this function. I, of course, would like the solver to be going beyond the gradients, because if the function is black box, it might not be differentiable, right? So we cannot assume that we can do differentiable stuff. So we need what we call a zero order method. So gradient first order, we need to go zero order method. And of course, we would need to be able to meet those constraints. So these are the properties I would like to get from my solver, right? So this is a function which is a black box, expensive to query. And therefore, I would like a data-driven solution which is efficient because of the expense of querying, and also might not necessarily be differentiable, and also it needs to be feasible with respect to the constraints. So, okay, I mean, you might ask, okay, fine, exciting problem, interesting problem. But now the question is why this is an important problem. So maybe I will try to motivate first why we need to focus on this problem from different examples. And then we go into techniques that allow us to solve this problem. So maybe the most common setup, right, for solving this problem is the hyperparameter optimization that is common in AutoML or in machine learning in general. So here what we have is we typically have a training data set, right? So maybe let's say a set of images. and these images are labeled, for example, or text, whatever it is. It's just the data set we have. And then what you typically do is you have a training algorithm. So that training algorithm, right, it takes a set of hyperparameters for the network that you are interested in. For example, the learning rate, the number of layers, the number of units, etc. And then the training data set. And then what it does, it actually works to minimize the loss. Now, generally, those hyperparameters, they are typically set by you as a user, given your experience, or you may be using grid search or whatever, right? What we are going to do is we are going to introduce a learner, an agent, that will make the action of the decision, what are the form of the hyperparameters. So now we have this entity, right, which is the agent, and it's deciding what hyperparameters I should put. Given those hyperparameters from the agent and the training data set, right, then we minimize this loss. And then this loss emits for me the optimal weights of my neural network, right? So this is what I call W star of my neural network. And then what I do is I take these W stars, and then I have a validation algorithm which will take the W stars that I trained, right? And then a validation data set. And then it will validate, the value, right, of the of how good these W stars I found were, right? And then it will return the feedback back to the agent. So now please notice the following, right? If you choose the wrong hyperparameters, as you already know, right, then you will have bad weights, bad W star, meaning that you will not have a good network, right? So now the question is, how do you pick the values of those hyperparameters? And now notice that it's very hard to do differentiation through the hyperparameters, because one, you need to differentiate through W star, which itself is an output of an optimization algorithm like Adam or something. And also the hyperparameters might also be discrete, right? Like number of units, number of layers, and so on. So you cannot really do differentiation. But what's even worse is that if you have a big network, one trial of this could take you a lot of time and a lot of money. So in other words, the data which we will need to collect in accordance to my problem I mentioned above is the set of hyperparameters as inputs and the value of the function, the value of this validation error. But as we said, there's a lot of expense here because one training loop is very, very expensive. So I cannot do so many trials of the hyperparameters. So this makes me, at least in machine learning, say that there is this setup, right, where this problem I mentioned above is actually important. And typically people who do Bayesian optimization, not all, but some, they end the story here and then they focus from here and onwards. One of the goals of this presentation is I would like to tell you that this problem of black box optimization is not only for hyperparameter tuning, but it's actually much bigger field that can be applied broadly. And I would like to give you some examples from industry that we have done where this problem popped up. So I will give you 3 examples. One of them is a logic synthesis problem, and I will describe what that is, then a maximum integer programming problem, and then an antibody design problem. So I'll be giving 3 examples to, again, motivate that this problem is not unique to hyperparameter optimization, but it has a broader applicability. So let's start with logic synthesis. So what is logic synthesis? What I show you here is the pipeline of how you would create a chip, like a microprocessor, right? So the idea is that you start from system specification, right? So somebody comes in and tells you, I want my chip to do this, to make it be a chip for a square root function or add 2 functions or whatever. And then from the system specification, you design a certain architecture of how your chip is. And then you write this in RTL language. But most importantly, there is a phase called logic synthesis, which will take your design and will actually try to map that into physical gates, right? So what it will do is it will take, what you thought the architecture of the chip should look like, and then it will map that into AND gates, OR gates, XOR gates, and connections between them. And then from that, we get the physical design. And from that moment onwards, we have many other steps that will at the end give us the chip. But this logic synthesis problem is actually a very important problem because it's kind of the connection between your ideas and software and actually the real hardware and the implementation of the chip. So how does that step work? Well, first of all, you take the chip. So here's an example of a circuit, that is designed, which has like, for example, AND gates and OR gates, right? And then what you can do is you can map this chip into a graph. So this graph is a description of this circuit, right, which is equivalent. So there's a theorem that says you can describe, these Boolean functions essentially as a graph which has only AND gates and inverter gates, right? So you could describe any circuit just by this, what we call AND inverter graph or AIG. Now, once you've made this, right, what is your goal, right? So now your goal is, because you want to manufacture this chip and you want it to be small, right, and things need to fit in certain sizes, what your goal is you want to apply operations on your original design such that you change, this graph, this AIG graph, to meet certain constraints about performance. So in other words, I will give you a bag of C++ algorithms, and those algorithms, they are operations on top of this graph. So for example, you can refactor a graph, you can resubstitute node in the graph, and so on. And then what you can do is you can apply a sequence of those operations on top of the graph, and you're looking for the optimal sequence and the optimal parameters of each operator in this sequence such that you maximize a performance criteria. So just to give you an idea that this is a messy problem, I just show you an example of one of those operations, right? So there's a library called NTK, which is a library for its logic synthesis, and it had implemented those operations that you can execute on the graph, right? So here I give you an example. So first of all, notice that this is no need to understand all the details, right? But the idea is that this is a C++ code, right? So there's no hope of differentiability through these things, right? This is a C++ code. And not only it's a C++ code, but it also takes configurable parameters. So for example, node size, cone size, update level, and so on. And these will dictate how this operator will act on the graph. So for example, if you pick a certain node size, it will only cut when it arrives to that node size. It will cut the graph. So I call this algorithm AN of theta n, meaning AN, just like one of those algorithms like refactor, and theta n is the parameters that this algorithm would take. And now this theta n is also mixed, like it could be continuous and discrete. So for example, you can have a number of nodes as discrete, but you can also have like update level, which could become continuous or floats, essentially. So now we are here, right? So we have this AIG graph, we have this bag of algorithms, and now my goal is I would like to find the sequence of those operations I can execute on the graph, right? So what to pick, A1, A2, A3, blah, blah, blah. And then also their hyperparameters, right? Like the node size, the cone size, etc. in order to maximize a performance measure, which we call QOR, quality of results performance measure. So what's this quality of results? This quality of results is a ratio between the area over the time delay. So the idea is that after you do this operation, you shrink your graph, right? And now you have a new area of the circuit. And then you would divide that by how much time it takes a signal to propagate through that circuit, and that's what we call QOR. So what we would like to do is we would like to maximize that trade-off between, area and delay. And of course, we have a certain constraints. So these constraints are, for example, allowable ranges of the sequences and the parameters. So not all sequences are okay, not all parameters are okay. So now my goal is I give you this AND inverter graph, right? And you need to find the sequence of operations on that graph and the corresponding parameters of each operation such that you maximize this quality of result and you meet the constraint. So what is the difficulty of this issue? Well, the QOR computation, so if you want to try one sequence, right, it is very expensive to do because in the real world, we have circuits that are with the billions of nodes, So now trying one sequence operation is extremely slow to do in real world validation. Two, as you see, when I apply those operations over and over again on my graph, right, then I have a nesting of these C++ codes, right? Because I do the first, then I do the second, then I do the third, and so on. So now it's very hard to do two things. One, to write a closed form equation of what's going on there, because this involves C++ nestings. And two, it's very hard to differentiate because even if you were able to differentiate, we are working in a combinatorial space. So there's no derivatives here that are nice to deal with. And of course, the constraints, they involve, complex algorithmic checkings, and they also are hard to get in a closed form. So now this example, which is an important example in, let's say, manufacturing chips, right, which is this logic synthesis, as I mentioned here, it is a problem which is a black box because we have, the nesting of these algorithms and the lack of nice differentiability properties. And also, it is very expensive to compute because, it's very slow when we want to do these things in the real world. So we're back to my original problem, which I said f of x subject to constraints, where f is a black box and expensive to evaluate as well as the constraints. So this is one form of an industrial application where this thing pops up. So let's talk about the second example to further motivate the beyond, let's say, the beyond hyperparameter tuning, and that is MIP problems. So what is an MIP? So I'm sure you've heard about MIPs, hopefully. So these are maximum integer programs. They are programs of this form. So you would like to maximize with respect to a variable x some linear cost or linear function c transpose x, where c are parameters dictating how the operation behaves, and then you have constraints of the form ax less than b. You have positivity constraints, but more important, what makes the problem difficult is that you have integer constraints. So your x values should be integer. Now it turns out that this problem has a huge applications in industry, going from production planning to scheduling to telecommunication, even to energy flow optimization. So now if we can solve this problem very well, right, we can enable many applications. Now, the point is this: over the years, this is a very old problem, right? And people have studied this for a very long time. So over the years, people have created different solutions to this problem and different heuristics that are capable of finding this variable x. So we're not going to try in now to create a new type of heuristics. We are happy with these heuristics, but we're not happy in how we combine them. So what we are happy with is, okay, we have these 100 different heuristics to solve the MIP problem, but now we would like to combine them or to make sure they work in a way we want them to work so that we get better results on my MIP solver. So to further elaborate this idea, let's talk about an open source solver called SCIP, right? Solving Constraint Integer Programs. So this is a solver where you can give it as an input an MIP task, so a maximum integer programming task. So you give it the matrix A, the vector B, and the vector C, right? And those, as you remember, dictate, this equation. So if you have vector C, vector A, vector B, then you can define the MIP problem. So we give this as an input, right? And then additionally, you give a set of hyperparameters, which are 200 parameters between mixed, discrete, continuous, and Boolean. And this SCIP will work on these two using the heuristics developed by people, like by researchers, and then it will output for you a feasible solution, X star. Now, two problems here. One, the choice of these hyperparameters, right, they affect your running times a lot. So if you choose them wrongly, you might still arrive to X star, but you will take hours to arrive, or even weeks sometimes, to arrive to X star. And two, they are very difficult to set by a human, by an engineer. So if you look, I'll just give you an example here of these SCIP. You see these have different parameters like separation parameters, branching parameters, LP parameters, and so on. And what is interesting is that those parameters, which are very hard to set by a human, they vary between, like real values, Boolean values, integer values, and even categorical values, right? So now the question is, how would we set those parameters in order to guarantee a specific property? So what we really mean is I would like to find those parameters theta, right, that will minimize the running time of my SCIP solver, or any solver for that sake. We just tried SCIP because I think it was used in one of the NeurIPS competitions or something. And then this SCIP has this parameter theta, and of course there are constraints about this theta. What are, for example, the constraints are this variable needs to be categorical, this variable needs to be Boolean, this variable is an integer, and so on. Now, again, this is a problem where the running time is very, very slow. Like, in fact, we tried this, and no joke, it could take up to days or weeks to solve a big enough MIP problem. Again, when you choose these theta parameters, you're actually nesting heuristics internally inside the solver, so it's hard to get a closed form equation. And as you see, it's very hard to differentiate this with respect to the parameters. One, because we don't know the black box function exactly, and also what is very interesting is that we have these different types, Booleans and categorical and so on. So it's very hard to actually do these gradients. And the constraints are easy to write in this example, but we also need to meet them. So again, this is a problem with broad applicability, which is a black box and also expensive to evaluate. And now that takes me to the third motivating example, and that is an antibody CDR design problem we worked on. So let us just talk a bit about what antibodies are and how they actually work. So by no means I'm a medical expert, right? But this has been done in collaboration with medical people. So they helped us understand, right, all these types of problems. But what an antibody is, right? An antibody is a Y-shaped protein that looks like this, like you see here. And that antibody has different chains inside it. So it has like a variable chain, and it has it has a light chain, and it has a heavy chain. And on the top of the light and heavy chain, there is a variable region. So what's that variable region? That variable region is a region which allows this antibody to actually connect to a specific antigen that would enter your body. So if you change that variable region in different ways, then you can actually specify that antibody to bind better with a specific antigen versus another antigen. Now, we call that region complementarity determining region, or CDR for short, right? Like CDR region. So the CDR region, what is really important for us here is that this is something we can optimize in order to, bind to a specific antigen versus another antigen, bind better for a specific antigen based on another antigen. So how do we construct this CDR region? Well, the CDR region, they are proteins, right? So as everything else in our body, or most things of our body are functional on, they are proteins. Now, those proteins, they are made from something called amino acid, right? I'm sure you've seen this before, but the idea of an amino acid is that this is a molecule which has an amino group, so of the form NH2, and ends with a carboxyl group of form of COOH. So there are 20 to 22 amino acids actually that comprise the proteins. Those are, for example, alanine is an example of it, cytosine, glycine, tyrosine, and so on. So it's not really that important to understand the exact details of what each amino acid is doing, but the whole idea is that when you chain these amino acids together, then you form proteins. So the idea is that when you put the two amino acids together, what will happen is the amino group, or the NH2 group and the carboxyl group will work together, and then they will form a peptide bond and emit water. And then you chain those together, like you chain them together, and then you will form a polymer, which is like the protein we are talking about. And now these polymers are typically made between 50 to 4,000 amino acids. And what's really important here to note is that the order by which you change things actually matters a lot. So what I show you here on the left is an order of tyrosine, glycine, phenylalanine, and leucine amino acid sequence. And that turns out to be an opioid, right? That modulates pain. However, if you just change the order of this, like go, for example, backwards, so you go leucine, phenylalanine, glycine, tyrosine, then this is a different molecule, and we don't know any more pain modulation effects of it, right? So the order by which we change those things, right, actually matters. So now let's go back to the antibody problem that we just described. So what is really our goal, right? So my goal, if we think about it, right, on a very abstract level, of course, is that I would like to find the optimal sequence of amino acids, that are on the tip of my antibody. Remember, we have this Y-shaped thingy here, and we had this tip on it, which we call the variable region, right? So now what my goal is, I would like to find that order of that sequence of amino acids, right, such that my resulting antibody will bind well to an antigen that has been introduced to my body. So in other words, what I would like to do is I would like to find the sequence, right? I would like to find the sequence of amino acids, right, which I call CDR sequence here, that bind well, right? So that bind well with respect to an antigen that entered to my body. So please notice this is antigen specific for now, whereby if you get, for example, some antigen, what we want to do is find that good sequence which minimizes the binding energy. And of course, right, we have constraints here and now these constraints are critical and they're very important because not every sequence is allowed. There are sequences that are hard to manufacture in the real world, which we don't want to get out of the algorithm. There are sequences that have very high toxicity, which we want to reduce as well. And we have sequences that have a hydrophobic constraint, meaning like dissolution in water, and we also want to constrain those as well. So now my problem here, right, is I would like to find a sequence, so minimize the binding energy, right, with respect to a sequence, CDR sequence of antigen subject to a constraint. Now, my sequence, as I told you, is just made of amino acids, right? So these amino acids, there are 20 to 22 of them, right? But remember, their order matters because I showed you this pain modulation versus non-pain modulation. So their order by which we deal with this thing actually matters. So now we have a combinatorial space. It's like a huge space. So the problem, again, is that the binding energy computation is extremely slow because you can do it in two ways. One is a real-world way where you actually create something, go to the chemist and tell them to do a wet lab experiment for us. And we're actually trying this now. But another way is to use like physics-based simulators, and these physics-based simulators are also extremely slow. And they are very hard to get in a closed form equation as well. And you're looking, like this is an analogy I like to make, you're looking for a needle in a haystack because you're looking for that sequence or maybe a distribution over sequences that actually from this humongous search space is capable of finding that right antibody. Right. Do I delete? Okay, so now I hope I convinced you that this problem is important. It's actually applicable beyond hyperparameter tuning. I don't know how it goes, but I'm happy to take any questions now if there are any questions before we go into how we're going to solve those problems. Are there any questions?
Everyone happy so far? Well, yeah. Everyone,
Okay.
Yeah, over there. But you have to speak up.
I think your function is very difficult to define. Yeah.
I couldn't hear you well. Could you repeat?
He was saying, he says that the function is very difficult to define.
Yeah.
Which function?
Yes, correct. Yeah, exactly. So it's very difficult to write down because it's complex, you know. So that's why we call it a black box, you know, because we assume we don't know it, right? So for example, take the antibody example, right? Like, what's that function? What's that binding energy, you know? I mean, in reality, it's the real wet lab experiment, and that's just very hard to write in a closed form because it involves a chemist, it involves some real-world stochasticity, you know, whatever. Or take this chip design problem, right? Like, again, the black box function is very hard to define because it involves this crazy nesting, right, of those algorithms, and then that's extremely complex to kind of define in a closed form, right? So it's not like, let's say, as a standard machine learning where we know the loss function and, you know, it's just like mean squared error or cross entropy or something. This is more complex set of problems where the function we do not know in closed form. And to add insult to injury, they are expensive to evaluate, and that's why, you know, like, we cannot even assume we have tons of data, you know, to deal with this problem.
Perfect, thank you. Any further questions at that point? Everyone seems to be very happy so far. You can go on. Thank you.
Okay, cool. All right. Okay, so hopefully I convinced you so far that the problem is exciting, right? Like, this maximize f subject to constraints. Hopefully we all hopefully agree by now. Okay, there's many applications of this. It's important problem. How are we going to solve it? Now, what we're gonna do is we're gonna design a data-driven solution. So our data-driven solution will look like this, right? So we will start with our agent, that's the learner, which will pick the variable X. It could be the hyperparameters. It could be the sequence in my CDR region. It could be the sequence of operators in AIG, or it could be the parameters of my MIP problem. So it'll just make the decision about, okay, what's the value of my parameters that I'm actually interested in? Then when it picks these parameters, right, we go and evaluate those parameters in the black box, right? And the black box will respond to me with a value f of x corresponding to those parameters that I have picked. So for instance, if I am doing this, let's say, logic synthesis design, right, I will pick the x to be like the sequence of the operators and their value. And then my black box will respond for me with this quality of result value corresponding to that x that I have inputted. Or if I'm doing hyperparameter optimization, this x will be the value of the hyperparameters, like the learning rate, the number of units, and so on, right? And then the black box will be, let's say, the validation loss that I will get corresponding to those hyperparameters. So my agent starts with this. And then after it starts with this, it goes over time. So it continues to interact, right, with this environment. And then as it interacts with this environment, it will start picking more and more of these x variables. And then the black box function will respond with different f of x. So x1, fx1, the first trial we did, x2, fx2, the second trial we did, and we did xi, fxi, the ith trial we did. And this is running over time, so I can, continue this loop. Now, people who know reinforcement learning, right, will look at this problem and say, so what's so special? Yeah, I mean, this is reinforcement learning. I'll just call X as my action, right, F as my reward, and then I'll just do some reinforcement learning on it, right? Okay, that's a feasible solution potentially if I allow you to interact a lot with your black box function. But since I want to be data efficient, then we don't think that model-free reinforcement learning in this setup is actually going to be the right direction that we should take here. So what we really want, right, is we want to design an algorithm that will improve the guess of my xi values, right? So I want to improve the guess of the optimum x star that I'm looking for, but I want to be data efficient, right, in terms of how many queries we can ask from the black box. Okay, so I want to find that variable x, and I want to talk to that function, but I want to talk to that function, to find X star. However, I don't want to talk a lot, right? I want to be data efficient. I want to reduce my sample complexity. Okay, so how would we think about this problem, right? Well, the simplest way, right, to think about this problem is, what if, right, we were able to build a belief model over what the black box function is doing, right? So if I am, from this data I have collected so far, right, I can build a model that will say, okay, for this X I did not try, I believe my f of X will be something like this. Then I can work with this model instead of working with the true black box, right? And then I can reduce my sample complexity, right? In order to, because then I can use this model to take actions or to find the X variable without probing or talking to the real black box function. So automatically, I have reduced my sample complexity, or the number of queries I'm going to make to that black box. So if what I'm really trying to say is that for me to be data efficient, I'm not going to rely on model-free thinking. What I would like to do is I'm going to try to rely on model-based thinking, where I'm going to try to build a model of the black box of the surrogate function, and then use that instead of talking to the real world, and see what I can do from there. Now, the question becomes, I mean, this is not a revolutionary idea, right? Like, I mean, it's very simple. Okay, we have f of X, we don't know, maybe we can model it and then use it in order to take actions, okay? But now the difficulty is that I cannot assume I have so much data, right, when I am modeling this function f of X. Why? Because, simply this function is very expensive to query. So what I really would like to do is I would like to build a model, right, that is based on small data, right, and that at the same time will tell me how sure I am about my prediction. Because if I know how sure I am about my prediction, then I can actually use that in order to decide, should I trust my model or should I try something new to get more information? So now I can trade off the exploration-exploitation trade-off, right, between trusting my model versus just exploring something. So two main ideas, right? One, I want to build a model which is a belief over the surrogate, which I will use instead of the real function that will reduce my sample complexity or reduce my number of queries. And I want this model to give me uncertainty about its prediction, so I know whether I should trust it or I should just explore some new X variable because I don't trust my model, so I can get more information in that area. So I summarize these two steps in this slide. So the first step is we're going to learn a Bayesian model. Why Bayesian? Because we want to also get this uncertainty I told you about, right? And two, I want to trade off based on my Bayesian model, right? The exploration exploitation, right? Now, what we call that trade-off in Bayesian optimization, we call it something acquisition function. We call it acquisition function, which is a formalization, right, of the trade-off between exploration and exploitation. And we will dive into each of those steps in a second. I just try to give you a general idea of why we are thinking in this way, right? Now, when it comes to the Bayesian model, we agreed we need two things, right? We need one, a low data regime operation, and we need uncertainty, good uncertainty estimates. And Gaussian processes, they offer us this ability. So this is a book of, well, I think it's the Bible of GPs. I actually think I have it here as well. So it's about Gaussian processes from Carl and Chris. And I think it's definitely worth a read if you're interested in any of this. And that will allow me to do a Bayesian model. And then to maximize the acquisition, I will talk about different type of acquisitions like expected improvement, upper confidence bound, and then this will allow me to do this trade-off. Okay, so two steps, right? First step is learn a Bayesian model. Second step is maximize my acquisition. Learning Bayesian model will allow me to build a belief over the true black box function with uncertainty that I will use to trade off exploration exploitation in my acquisition function. So now let's dig a bit deeper into each of those two. So I'm going to be giving a very brief introduction to Gaussian processes, just something that is needed for the remainder of the talk, really. It's a much bigger field. It's just I'm going to just mention teeny tiny things. I'm probably already encountered Gaussian processes before as well. But now, first, before I start, I would like to thank some colleagues that allowed me to use their slides and their ideas. So some material is borrowed from James Hensman, Rich Turner, Nando, and Neil Lawrence. Neil and Nando, I took there from YouTube. James actually shared with me slides as well as Rich, so I'm very grateful for that. And I'm going to be using, I think, Nando's way of thinking a little bit to explain what the Gaussian process is. So the story of, for me, that's easier to understand for Gaussian processes starts from simple Gaussian distributions, right? So as I am sure you already know, that a Gaussian distribution is this bell curve, bell-looking shape thing, right? So this is its equation, right? So it has this equation, 1 over sigma squared root 2 pi, x of minus 1 over 2 sigma squared x minus mu squared, where mu is the mean and sigma is the variance, right? So the mean is where this bell curve is centered, and the variance is, kind of its width for that bell curve. Right, so that's the simple bell curve Gaussian distribution we all know in 1 dimensions. Now, we can extend that into 2 dimensions, right? So, or not 2 dimensions, so we can extend that into higher dimensions. To extend that into higher dimensions, let's think what we need, right? I mean, if we look at this bell curve, right, we notice it has a mean, right, where it's centered, and it has a variance, sigma. Now, if I'm in higher dimensions, right, my mean cannot be 1 point because, it's a higher dimensional space. So my mean needs to be a vector of points. So I need to say where this distribution is centered along this axis versus any other axis in any dimension I'm working with. So therefore, I need a mean vector and not a mean value. 2, the variance, right, it's studying the variation, right, of this